In this work, we propose NAS-DGCNN, a novel one-shot NAS method for efficient point cloud processing. We focused on adjusting the architecture parameters of the network to improve efficiency. Point clouds provide rich information for a better understanding of the surrounding environment for machines. Existing point cloud models are designed with complicated feature extractors and network architectures, which causes high costs on computing and storage resources. The computational bottleneck prevents these models from being deployed in various resource-limited devices. Neural architecture search is a common technique for compressing a model. However, applying NAS to point cloud processing suffers from two problems. First, most of the NAS methods are designed for 2D vision recognition and ignore point cloud operations, such as point grouping, which limited their application in point cloud processing. Second, some NAS methods for point cloud processing aim to achieve higher accuracy by neglecting the various requirements of computational resources. How to discover a compressed network for point cloud processing is not well explored. To this end, we propose a one-shot neural architecture search method for point cloud processing to achieve efficient inference and storage across various constraints. We establish our point cloud network based on DGCNN. We designed 3 supernets with different sizes for classification and segmentation. Specifically, the classification supernet Tiny aims to find an architecture with a tiny model size. The classification supernet Base discovered a network in a larger search space. The segmentation supernet enables searching for different dense prediction models. The size of classification supernet Base and segmentation supernet is the same as DGCNN. These supernets contain 3 kinds of searching space: point grouping, network depth, and channel numbers. Previous point cloud networks are proposed to dynamically calculate the nearest neighbor to obtain dynamic graphs with the fixed number k at each layer. However, determining k at each layer is not well explored. We propose dynamic point cloud grouping to support dynamic adjustment of k to help network learning point representation with variable size dynamic graphs. Dynamically adjusting k can allow the network to learn essential information, making network depth scalable and reducing the number of channels can produce a compact network. As a one-shot NAS method, the weights of the selected blocks or channels are shared between architectures of different sizes. We train the network using progressive stage training and knowledge distillation. Then, we employ a random search to sample subnets and evaluate them without fine-tuning or retraining. To alleviate interference between different subnets, we train the network progressively, in sequence from large to small subnets. Specifically, we first train an entire network from scratch. Then, we randomly sample a subnet based on the specific search space at different stages in each training iteration. In the classification task, our method achieves a maximum overall accuracy of 93.4%, which has comparable or better performance in smaller sizes than most hand-designed state-of-the-art networks. We achieve a computation compression ratio of up to 17.5 times in the classification supernet Tiny compared to the original network while maintaining the same level of accuracy. For part segmentation, our method achieves a maximum MIOU of 85.4%, outperforming the original DGCNN segmentation network. Within a 1% drop, we compressed the network by more than 2.7 times the number of parameters and 1.8 times the amount of computation. Thank you for your support of our work.